Going back to our data, let's consider how good fitting a horizontal line to the data will be. Let's choose a horizontal line whose value is the average of the data. The average is obtained by summing out the individual y values and dividing by the number of them. In this case, our average is 34. Plotting the horizontal line in red, we can see how good it is in predicting the impact strength. For example, when x equals to 15, the horizontal line will predict a y value of 34. This value is 8 less than the actual y value of 42. On the other hand, when x equals to 25, the horizontal line will again predict a y value of 34, which is the same as the actual y value. The difference between the actual y values and the predictions tell us how good the fit is. In the table, these differences are calculated, where we take each of the measured y values and subtract 34. If we sum up these differences, we see that we will get 0. This is what the average gives us. It balances the overestimates and the underestimates. Since the sum of the terms are 0, the sum is not very useful in telling us how good the fit is. Logically, overestimating the data is just as bad as underestimating the data. For example, having an overestimate of 8 should be penalized in the same way as an underestimate of 8. Taking the square would enable 8 and minus 8 to give the same value of 64. Hence, instead of using the sum of the difference to tell us how good the fit is, we will use the sum of the squares of the differences. Each of the differences is now square as shown in the fourth row of the table. Notice that all the values are now positive numbers. Next, these terms are summed up. The value of 114 tells us how good the fit is. The larger this value is, the more overestimation and underestimation occurs, and the poorer the fit is.